Hmm? Hello. Test. Hello.
Hello,
Hello.
Dr. Cheng.
Hello, can you hear me?
Yes, I can hear you fine. Can you hear me?
Yes. I can hear you too.
Okay. So, have you met Katerina yet?
Um, so I didn't meet her using any apps. We just contact using emails.
I see, because normally she starts the room so she can organize
Oh,
it.
I see. Is there any way I could change?
Well, we could close the room, but let me try to just ping her in.
Oh, okay.
Because we're supposed to start in about 10 or 11 minutes. So,
Okay, let me maybe I could leave quietly and someone could
um,
it says if I leave, a new moderator will be chosen from the current speaker. So I
well,
guess
let's.
when she joins, I can give her.
Okay, well, what would also be nice is if you could make me moderator. If you click on my picture and there's a button that says make moderator.
I see.
Hi, everyone.
Oh, hey, here you
Already
are.
here. Sorry.
I was just pinging you. Okay.
Thank you. How
Okay,
are
so we were discussing whether we need to restart the room, but we're all here in mod, so is that okay?
Yep, yeah, sure.
Okay, we're good.
Good.
Dr. Cheng beat us to the stage.
Thank you. Uh, you still know where the unmute button is, right? Just in case. Uh,
Ah,
hey.
yes. So I just mute myself.
Yep, exactly. Thank you. Uh, thank you for opening up the room. How's your Saturday? Everything good?
Yes, everything is good.
Let me put up the PowerPoint. So you can click on, we can click on it and try it out just in case it should work. Let's do that.
So, Dr. Cheng, this is a really fascinating topic to me. My background is in chemistry, and I do dabble in AI lately, much more. So, I'm going to be very curious about your topic.
Thank you.
Hi. Yeah, as well. I mean, this is a very interesting topic. Looking forward to the discussion.
Hi Frank, how have you been?
I don't know if I was heard. I have a problem with the signals. I just said, very looking forward to this very interesting discussion.
Yeah, we could hear you. I hope you can hear us. But
Yep.
yeah, yesterday we had some issues in the room yesterday. On stage, apparently not in the audience, but on stage, sometimes people would be cutting out, but not for everyone. So it was kind of
Oh,
weird.
yeah, it was really sort of this stochastic, connection drop. It was crazy.
Hey everyone, hi Dee, hi John, hi Rabbit. We'll start in around 6 to 5 minutes. Thanks for being here and yeah, welcome.
I'm going to sneak bites.
So they limited the pinging quite harsh. Did you realize you can only ping like a few people?
Oh, did they cut that down?
Yes. So could only ping now a few people in. And people always tell me, please ping me in when you have a room, but I can't possibly ping everyone in. Hi Ben. Hi BA. How are you today? Yes. Something. Did you do something nice today, Serena?
I did. It was, did I already forget? No, there
Yeah.
was something really,
Oh, go ahead.
oh my God, well, I just saw a show with Chris is over, so we just saw a show, but what was I doing this afternoon? I already forgot.
Yeah, happens. That
It's so
happens all.
funny. Oh, and I forgot my PTR. That was Victoria invited me into one of her sound rooms, and I thought this was more appropriate. I think I'll switch back though.
It's nice. I like it.
Do
I
you?
mean, I like also the other one. I mean, it's hard
Yeah,
to decide with your pictures, but
this is my noir one. I think I'll switch to my regular one.
yeah, it's nice. The light is nice, you know.
It's funny that that's actual sunlight, and then I used a studio light filter and put a vignette around it. But that was the sun coming in, so it was kind of funny.
Yeah, it's nice. I have to switch it up, but it's so hard for me. I don't like pictures of myself, so it's really rare. Hi, Mona. We'll start in around 3 to 4 minutes. Welcome, everyone. This will be a really exciting talk with our guest speaker. I'm sorry, I want to check if I'm saying your name right. Li Shui Cheng? Is that right?
Yes.
Uh,
My Chinese name is a little bit hard to pronounce. You can
oh,
call me Sherry. It's fine. If you.
oh, but yeah, if I'm not saying it wrong,
Yeah, yeah. Of course, you're saying it correctly.
It's
yeah.
Li Shui.
Yes.
Li Shui.
Okay,
力学
Li
Yes,
Shui.
yes. Sure.
Okay, Li
Mm.
Shui on the
Li
I.
Shui. Okay,
Thank you, Frank. Nice.
Yeah, that X is hard.
Li
Thank you.
Shui.
So what would
Okay.
be the Chinese English translation? I mean
I think the
uh,
closest
beautiful
one
snow. Is that
would the closest one be Lisa, I think.
Maybe, but yeah. So I used Sherry for a very long time. So that's my uh English name. But yeah,
Sherry?
here, yes. So that's my English name.
Okay.
So I think it's also on the slides, the first page.
Whichever you prefer is the name we'll go with. So I know how it is. My name rarely gets pronounced right. So
Yeah, I guess Sherry probably is better.
I actually, it's funny when sometimes people then actually pronounce it like, you know, people in Portugal would. I feel like happy all of that. It's so weird. Uh, you know, when somebody pronounces your name like when you were a kid, then
Well, have I been doing it right all along, Katarina? Is that how
oh,
you say it?
It's fine. It's Katarina, but it's hard to say it that way. But it's not
Katarina.
wrong how you say it. It's totally not.
Catalina.
Yeah,
Katarina, right?
yeah. It's not wrong. It's right. It's the right spelling. But mostly Russian people say completely right, so it kind of makes me happy. I don't know.
I could put a Florida spin and say Katarina.
Oh, right. That's also cool.
Hello there, Katarina.
That's cool. I like that.
I'm enjoying living in Florida. I get to be one of the tribe.
So how long have you been in Florida, actually?
I think we're going on 4 years.
Oh, wow. Yeah, that's a
Yeah.
while.
Because like 2 years went poof. Funny how that works.
Yeah.
Yeah, it's about 4 years.
Then you start feeling at home, right?
Yeah, it's been long enough where I kind of local. Well, okay. Shall we?
Yep. Welcome everyone to the Science Society, and of course a special welcome and thank you to Dr. Li Shui Cheng, and she will presenting here her very interesting research. She is in the Miller Group in the Division of Chemistry and Chemical Engineering at the California Institute of Technology, and she did her. She will actually join soon the Tencent Quantum Lab in July 2022 as a research scientist, and she earned her PhD degree of theoretical chemistry in California in the California Institute of Technology, where she worked with Professor Miller, and she received her Bachelor of Science degree in quadruple majors in chemistry, math, biochemistry, and molecular biology,
Oh my
and
God.
a minor in computer science from University of Wisconsin-Madison. She is interested in the interdisciplinary research between chemistry, physics, biology, and computer science, and is passionate about bringing the mind gaps between different areas. Her current research focuses on AI for chemistry, including molecular modeling by molecular-orbital-based machine learning, methods for electronic structure and nucleic acid secondary structure modeling with machine learning and molecular dynamics tools. So, yeah, you will have such an impressive bio. So, it's really an honor having you here. And if it's okay, Serena would ask you a couple of questions, and then it would be the stage is yours for your presentation. Is that okay?
Oh, of course, of course.
Okay, well, welcome to the Science Society. We like to ask a general question in the beginning. And was there a time where in growing up, was there a time where you really, or a particular moment where you really knew you had to get into science?
I think probably high school. Yeah. So high school I read several books, college textbooks, and find it fascinated by the biology and chemistry these topics. And I think if I have an opportunity, I want to keep working on these science majors and keep developing all the techniques in these fields.
Mm-hmm. So, and you got into, I heard that you cleared a quadruple major at once. That's so fascinating. What was it that brought you to the particular study of understanding molecular orbitals through AI approaches?
It was my first year graduate school, so I'm the nearly the only one that knows machine learning techniques in the group, and our postdoc has a very nice idea about how to about molecular orbital applications. And we start this work together. So originally, this using this molecular orbital idea is not only my idea. It's a kind of like a teamwork. So
Mm-hmm.
the initial goal for us is to bring down the cost of all these expensive quantum chemistry computations,
Mm-hmm.
to make everyone's research faster and more accurate. And we keep working on this field for a very long time, so nearly my entire PhD. And I find it's really useful too. So that's why I would like to keep working on this.
Well, it's an exciting application for a very recent field. So or approaches. Well, so the audience can access your talk, the slides at the top, and they can follow along. So you can either take questions at certain key points in the talk, or you can get through the talk and ask questions. It's really up to you. But
Yeah, of course.
okay, so with that, take us away.
So I think if anyone has questions, please just directly ask me during the talk, because I think it is easier to build up the ideas. If you ask at the end, maybe it's a little bit hard, maybe lose track. So I'm fine to be interrupted. Just feel free to interrupt me. Um, so
Hell yeah, that's awesome. Just want to say interruptions are really awesome, and if for those of us who interrupt you, my apologies even now as I say this, but I really appreciate that because I think oftentimes maybe more than one person has that kind of similar question or similar wrong idea, and so we can oftentimes address it. So no such thing as maybe stupid questions. So if anyone from the audience would like to come up and ask some questions as things go along, please feel free to raise your hand. And my apologies. Please go ahead.
Thanks for the demonstration, Eric.
Hell yeah.
yeah, uh,
Consider Exhibit A.
yeah. Thank you all for your invitation and introduction, and also thanks Serena's question. So today I'm introducing my research on accurate and transferable molecular orbital-based machine learning for molecular modeling. So if everyone could go to the page 2. So I hope to start with to introduce some basic current status of this general field of quantum simulations. So basically, the goal of the quantum simulation field is trying to solve this top equation called Schrödinger equation. So this is the general goal, and we want to solve this Schrödinger equation and find the energies of any chemical, biological, or material science systems. However, they directly solve this equation is super expensive, or sometimes it's even impossible. So people in this field developed a lot of different types of the theoretical approaches to solve this Schrödinger equation. And here I list a bunch of famous ones that people are commonly used in this field. And here I have a triangle from the bottom to up is increasing cost and increasing accuracy of these quantum simulation theories. And from the bottom to up, it also have a reduced largest size that a theory can treat. So basically, if you're trying to use a theory called Fusi, which is on the top, you can only solve very small systems like very few electrons. But if you have a classical field, you could simulate a very large system, like a large material or large systems, or like a protein. However, you cannot do it with the Fusi theory. So this is the current status of the methods. And here, I want to highlight a category of method, which is what we are trying to trying to targeting on. It's called the wave function theory, which is in the middle. is considered the second best category of the quantum simulation theory. This type of theory we could further develop a lot of subcategory of it. So here I list 3 of very useful theories in this category. From top to bottom is the CCSD Francis T, which is the golden standard of the entire field. So basically, if you run a computation and this is at this CCSD Francis T level, people will consider your calculation is very accurate. And then is a little bit cheaper method called CCSD and another method called MP2. All 3 of them is based on another theory called Hartree-Fock theory. So basically, when you want to compute the 3 theories I listed here, you need to first compute this Hartree-Fock theory, and then you need to do something on top of your calculation of this Hartree-Fock theory. This Hartree-Fock theory usually is much cheaper than the all 3 above, and it falls into similar cost as another very famous category called DFT, which is the most commonly used in the chemistry or biology world to do all the simulations. So the Hartree-Fock theory is very similar to DFT, but has a less accuracy than DFT. That's why people is using DFT to do all the quantum simulations, because it is cheaper and relatively accurate. So today our topic is trying to reach the high level accuracy of the 3 level of theories I highlighted here: CCSD Francis T, CCSD, and MP2, using the cost of this Hartree-Fock. So I hope this is clear to everyone. So if we are fine, we will go to the slide 3. So when after we clear what is our goal, so I want to also introduce a little bit of provide everyone a bigger background about the entire field of machine learning for quantum chemistry. So because we see that pyramid, you have different level of theories and you have different accuracies. People think of using machine learning to reduce the cost and improve the accuracies in the entire field, and people do have a lot of successful theories. So on the left column, I list the usual strategies in this field people are using. That people are using the geometries of a molecule or a system to generate something called features. Basically, your input X to make a prediction of the energies at a DFT level of accuracy. So usually people will using the numerical representations of the atom depths, bond types, bond angles, bond length. And recently people are using something called fragment motif. So basically, if you see OH is a commonly show up functional group, people will bundle them together as one subunit and do some numerical featureization or numerical representation of this subunit. So here I show an example of water. So and I highlight several things that people might consider to use in their representation using a geometry. So the benefit of this Euro strategy in the field is it is very easy to understand for general people, that I just directly using this geometry. However, so it has a very the accuracy of this strategy is not very good, because the map between this geometry representation, basically these bond types, bond angles, directly to that energy that we are targeting to, is less direct, which means that your machine learning map is very complicated and hard to learn. And also, there is another more serious issue of most of the methods in this field is they are less transferable. Transferable means that when I learn a small molecule, I could apply a similar large molecule, this model to a similar large molecules. Say for example, I learned a model on ethene, which has 2 carbons, and I want to predict an alkene with 10 carbons. So it cannot do it. But the idea is that for these small molecules, we can always calculate the energies very accurately. Another goal for this field is we could compute a very large system with a very high accuracy. But if your model cannot be directly applied to these large molecules and can only be restricted to the small molecules, that's a big loss for the for the for this machine learning approach. So to solve these issues that I mentioned in the Euro strategy, we come up with a new strategy that is using the molecular orbital-based features that is computed from that cheaper Hartree-Fock calculations. Recall that I mentioned that Hartree-Fock is a required computation when you do a very accurate molecular energy computation. So our idea is that we use some information extracted from these first computations that you made, and predict the differences between of the Hartree-Fock theory and the target theory, that golden standard we are happy with. So the here I show the molecular orbital. What is a molecular orbital? Because we are general audience, so I want to be more specific. So molecular orbital, if you naively thinking about it, it's like a bond. So if you have a OH bond, that's a sigma orbital, and if you have a carbon double bond, that will be a pi orbital. There are different types of the orbitals. And here I'm showing the 4 molecular orbitals in the water. And here we see the first one along the upper left corner is the OH bond orbital. And the second one is the OH bond orbital 2. And for the bottom 2, they are the lone pairs, because oxygen have extra two pairs of the electrons. So these are the lone pairs orbitals for the oxygen. So these 4 orbitals can also fully represent the water, other than the left column that I showed the purely the geometry. So we are using a numerical representation of these 4 orbitals to represent water instead of the geometries. And the benefit of our method is it is more direct, because you compute all these orbitals from Hartree-Fock. It honestly reflects your wave functions, your Schrodinger equation. So recall that we are targeting to solve the Schrodinger equation. So that phi is the wave function. So these molecular orbitals could represent these wave functions. So therefore, it is an easier mapping. And also, this way, it is transferable. Because if you think about the bonds, OH bonds in water actually is very similar to water bonds, to OH bonds in methanol or some other molecules. So molecular orbital is a general language in the chemistry field. So that's why it is transferable. So when you learn a small molecule, you have ability to predict a larger molecule. So I will show several examples of how it works and what's the performance. So I hope everyone understand the general idea and the motivation of our design. So please let me know if you have questions for slide for slide 3. If not, let's keep moving on to slide 4. So, like I mentioned in slide 3, we want to use a molecular orbital representation. But you see that the molecular orbitals are just a picture or shape. We need to have some real numerical representation. So basically the numbers, how to transform them to numbers. So here comes to how we design these representation, or design these features to faithfully represent all these molecular orbitals. Before that, I want to first introduce some physics related things to help us to understand why we do these feature design. So the first thing I want to introduce is about the factorization of energies. So like I mentioned, the goal is to predict the total energy of a molecule. However, these total energies could be separated as two components. The first component is what we do in the first stage of computation called Hartree-Fock computation, which is this EHF in slide 4. And the other component is called correlation energies, which is the EC in this slide. And the total energies could be the sum of both of them. So that's another reason why people could do Hartree-Fock on computations first, then do the golden standard CCSD process T, because actually it's built on top of it. And everyone can treat it as a correction. So Hartree-Fock is a baseline method, and the advanced methods are a correction based on the Hartree-Fock. And we are targeting on this correction term because we computed the Hartree-Fock already. And this correction term could be further decomposed as a summation of molecular orbital contributions. So this summations is epsilon ij. Ij is the molecular orbitals index. So for example, for the water case, we have 4 index. I could be 1 to 4. J could also be 1 to 4. So these are refer to the I and J refer to each molecular orbital. And for epsilon ij, it could also account for the interactions of 2 molecular orbitals, basically interactions between 2 bonds. It is very important to include these interactions because when you study some biomolecular systems, these are actually affect a lot of process reactions that we could think of. So, and this decomposition of the correction term correlation energy is called Nesbit theorem. So this is an existing theorem not developed by us. It's developed by Professor Nesbit back to 1950s. So that's he states that for any correlation energies, you could rewrite this correlation energy as a summation of the pair energies. The pair energies is the epsilon ij. So our targeting learning is become then to learn this pairwise decomposition, the pair energies instead of the total energies. And these pair energies, like I said, is a molecular orbital based. So basically, each pairwise molecular orbitals will have an identical pair energy. So we could do the machine learning by mapping the molecular orbital properties with these pair energies. And by the Nesbit theorem, this function, this map should be a universal map that basically we learn a function, as long as you give me a pair of orbitals, we could directly give you a unique and accurate pair energies. So therefore, we are trying to construct a map between the molecular orbital based features to the molecular orbital based pair energies. So I hope this sounds very rational. This rationale sounds very reasonable to everyone. So here then we could introduce our feature design, how we could do the numerical representation of these molecular orbitals to construct this map. I highlight several desired properties that we need to satisfy in this field, and I have several things in bold. This bold fonts text are the special properties that only molecular orbital based machine learning, our approach, satisfy, and a lot of other approaches didn't satisfy. But the more things or the general desired property are highlighted here also. So firstly, the things should be first principles. So basically, what is the first principles? Is that all your features should be computed or directly derived from your geometry or your related quantum simulations. And secondly, uniqueness. That for each molecular orbital pair energies, you need to have a unique representation. And for each representation, you need to give a unique prediction. And also, we should consider to have a consistent ordering of our representation. So basically, in each position, each feature represents the same physical meaning. Instead of we just throw a bunch of numbers and let machine learning figure it out. And also, we need to consider an important property in the quantum simulation called size consistency. So size consistency means that when you have two molecules in your systems, when you have two molecules very far away, say 1,000 angstrom far away, that they should have no interactions, and the total energy of the entire system should equal to the sum of these two molecules computed individually. However, a lot of theory cannot do this. This sounds very easy to do, so it sounds naive, but actually it is hard to satisfy. So this property is called size consistency in the entire field. Also, there are several invariances that we need to satisfy. So for example, translational invariances, basically when you move your molecule from one position to the other, your energy should never change. So this is the translational invariances. And the second one is the rotational invariances. So basically when you rotate your molecule, your energy and your features should not change too, because you just simply do some rotation, right? And also atom index permutation or orbital index permutation. So basically, it depends on if I label oxygen as 1 or label oxygen as 2. It should not affect my prediction for the energies because it's always the same molecule. So these are very important properties that when you construct a machine learning model, you should consider. And for the real features, we inspired by the MP2 equation. I recall that I introduced MP2 is a very important theory in wave function theory category. And we actually inspired by this MP2 equation to construct our features. MP2 equation I listed here in the slide 4. And in the bottom, we see 4 terms: FAA, FBB, FII, and FII, and FJJ. These 4 terms, A, B, has index A, B, I, J. These A, B, I, J's are actually the orbitals. And for the F, it refers to a matrix called Fock matrix. And this Fock matrix, people probably can find that Hartree-Fock also has a Fock inside of the name. So the Fock matrix is directly computed from the Hartree-Fock computations. So when you compute MP2, these matrix elements that directly computed from Hartree-Fock shows up in the computation equations. And for the upper one, that is the full index electron integrals, it is probably more complicated for people to understand. So I will waive the introduction of that. But people can just think about that the other 2 matrices can approximate the upper part of this MP2. And these 2 matrices are the column matrix and exchange matrix, which are also could be directly computed from the Hartree-Fock theory. So basically, then we have all the information or all the ingredients that we need to build up our molecular orbital features. That we just using these feature elements from the matrix and do some proper flattening operations. Then we could form a vector for each pair energies. And here I also show the benefit of doing this. So in the bottom, and I show the energy breakdown and the computational cost for the series. So Hartree-Fock can obtain or capture over 99% of the total molecular energy. But in the second figure, on the CPU time, people probably cannot see that blue part because Hartree-Fock takes only 1% of the computing time. So that's why it's nearly hard for people to see it. But for the part that the correction or the correlation energy that MP2 or CCSD or CCSD parenthesis T captures. These are very important for understanding the chemical process or chemical reactions, because it might change a lot for different structures or different processes or different reaction intermediates. So that's why to get this correlation energy is super important. But Hartree Fock is super cheap. So that's why our approach still have a huge benefit, because you cut over 99% of the cost, but you get exactly the same accuracy as what you are targeting to. So I hope the slide 4 is also very clear to everyone about how we design the features and how we have the idea where we come from. If there is no question, I will move on to the results part to show some
Um,
examples.
Dr. Chen, thanks for the excellent prepared slides. And for this particular slide, is just for me, I mean, it's overwhelming for me. I'm giving a layperson background. But can I request that you go a little bit further in explaining the in on the left you have a theorem that's saying that what is the energy here, the pair energy, what do any like physical uh, 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 thing that it points to? And then for the features, the could you go a little bit further to say what for the MP2 and can you explain again what's so basically, what is the connection between what is the features exactly? I mean, at this point, in my mind, it's just you have desired properties, but I couldn't, form get a comprehension of the particular features that you're generating. Yeah, thank you.
So for the features, I think I listed here is the matrix elements. That FAA, FBB, FIA, FJG are also the features directly. So the matrix will have, it's a 2x2 matrix that for each column and each row, it will represent an orbital value inside of the matrix. So I didn't write a full list of the features because I think that's too advanced for a general audience. So that's why I just listed that these are the matrix elements. These are just the matrix elements we directly obtained from the Hartree Fock computations. I hope it is clear, because I mean we have over 700 features, so it is impossible for me to write everything on the slide. But it's just an idea that how you could generate these features, because there are too many. And for the energy part, the pair energy is that epsilon ij. It represents the contribution and the interactions of each MO and the MO interactions. So if you think that you could chunk this molecule into different pieces, each piece will carry some energy. And if you think of like that, so the pair energy is for that each chunk's energy. That's why when you do a summation, you could sum them up and get the correlation part. Is that clear?
So we're only considering pair correlations here.
So I could be equal to J. So when you have I to J, that's also included. That's a self interaction of your MO. So MOI interact with MOI. So this Nesbitt theorem is exact. So there are long derivation for how you could from this correlation energy to this summation of MO decompositions.
I see. Thank you. So, just quickly, by the way, what is the shorthand for OCC?
That's the occupied orbitals. So I think I didn't explain that. If I feel that's a little bit advanced, you could ignore the following part, because that probably will not affect your understanding for the entire work. That for the molecular orbitals, there are two subcategories. One category is called occupied orbital. So basically, you have electrons in these orbitals. And there is another category called virtual orbitals. Basically, you don't have any electrons inside of it. And usually, we denote the occupied orbital using I and J index. And for the virtual orbital, which you can see in the MP2 equation, there is a VIRT, VIRT. We index it with A and B. So these are different subcategories of the orbitals.
Right. So then my confusion comes from the MP2 equation that you have occupied orbital summation index I and j, and then you have the diagonal terms that so the A and B is the for the virtual the new one. That's where I'm
The
confused.
A and B is for the virtual orbitals that you actually don't have electrons inside of it. And for our modeling, we only separate it as the mission of occupied orbitals, and then we could predict the occupied orbitals pair energies using the features that include the information from occupied orbital and virtual orbitals.
So I'll just say a couple of things that will maybe clarify this a bit for Hansen. In quantum theory, there's where an electron's wave function is in a given state, but and this is what the configuration interaction calculations that were mentioned earlier. Actually, there is additionally density in excited states that affects the density in the lower energy states. And so to calculate energies of molecules, and especially molecules interacting very accurately, you need to take into account the energy that those potential excitations would have on even the ground state as a correction.
Oh, so the virtual here meaning that the unoccupied.
That's right.
Yes.
Got it. Okay. Thank you.
Yeah. Sorry. I was thinking that probably it will be a little bit advanced for us, and actually it will not. If you didn't quite understand, it will not affect the understanding for the following things, I think. So so
Uh,
so
is this a?
go ahead. Oh, go
Oh
ahead.
yeah. So, is this a good time to ask a few questions, or should I wait till the end?
Oh, sorry, I didn't hear you very
Oh,
clearly. Could you
okay.
repeat?
Okay. Anyway, I'll just ask the question. The so I'm just wondering the computation, is it trained on the, is this first a few questions. First question is this neural net trained on the computation, let's say maybe a full-blown computation on density function theory? Second question, well, maybe I'll ask the first question first, and then I'll ask the follow questions.
Actually, no, we are not targeting to density functional theory, and also we are not using neural net. So I will introduce the machine learning techniques we're using in the following slides. We're not using neural net because neural net work requires a lot of data. So recall that our goal in this approach is to targeting very accurate theory, which you cannot always get a lot of points because they are expensive. So, but yes, we're targeting to the computations of high-level theory computations and using a cheaper computations to approximate it with machine learning.
Okay, so basically, so you're not using density function theory, then what kind of, so you're making a kind of a bit
So
rougher
Hansen, yes,
approximation?
she mentioned in the previous slide, it's a Hartree-Fock basis and the exchange correlation terms on top of that. So it's at a higher level of theory than density functional. But perhaps we could get a little farther into
I
the
don't
talk.
think Hartree-Fock is kind of a bit lower. I mean, because it
It's
just
more
picks
accurate
pair.
than density functional. But perhaps we should get.
I'm not sure about that. I mean, because Hartree-Fock is
We
basically
can go back. We can go back to slide 2 actually. So we are using
okay.
Hartree-Fock, which is less accurate than DFT,
Yes,
but we are targeting to
exactly.
CTST
That's what
Francis T.
that's what I'm saying. The Serena is saying that's more accurate, but that is because density function.
Yeah. So the final goal is to be more accurate than DFT.
Yeah.
So the
The
final goal we are
Hartree-Fock
targeting to
itself.
is CTST Francis T.
Yeah, Hartree-Fock
But we're
itself
using
is not.
Hartree-Fock.
Yeah,
Exactly.
with the exchange correlation terms, you can do better, but it's more expensive to compute.
But that's not an accurate
Okay,
statement saying
perhaps we could
Hartree-Fock.
move further into the talk, Hanson.
Okay, so but I just want to so the density function theory. I mean the exchange correlation, that's a correction term on the Hartree-Fock. So but that's not like as detailed as the function density function theory. But anyway, go ahead. Let's go
So
forward.
if you want to learn a B-Lab, you could also do this. So so basically, like you said, that B-Lab has usually have 20% of Hartree-Fock correction in the exchange correlation term. And if you want to learn the DFT, you don't need to do Hartree-Fock computation. You do XTB. Come back to the slide 2. That you could do a semi-empirical method and climb the ladder, climb this pyramid with a cheaper theory. It's no means for you to do Hartree-Fock and then predict B-Lab, right? Because they're nearly the same cost. So that's why we're here. The work I'm introducing is climbing between climbing between the ladder between DFT and the wave function theory. But if you're targeting DFT, you could also do a similar work like what I'm introducing here, but using a semi-empirical method, which is much cheaper than DFT. So you have variation of ways using similar ideas, and you can also using AMO based ideas using XTB, which is a semi-empirical method, or you can also using AO atomic orbitals. But these are not quite related to today's talk, so that's why I didn't mention that. So you have different ways to tackle that too, if you want DFT.
Yeah, no,
Just
I
quickly
agree.
with the
I
on the
just want to
slides.
make sure that what
So
the
this
base is.
Yeah. So our baseline, our target is CCSD, parenthesis D, and CCSD or MP2, not DFT. We're DFT cost. We are at DFT cost, but you can do better than DFT. So hope that's very clear to everyone now. If I want to
quickly,
explain,
so for this particular slide, is there a reference or this is your contribution? This pyramid hierarchy.
so you mean the papers we published?
No, I mean this particular slides number 2 with the pyramid hierarchy is the overview.
Yes, I made this pyramid. So, but I think if you check, you just search online and for any textbook, it will introduce that cost. So basically, it's the complexity. So for full CI, it's a computational complexity. So n factorial. Wave function theory, it depends on which theory you're using. CCSD process T is a complexity of the n to the 7th. CCSD is n to the 6th. MP2 is n to the 5th. DFT is usually n to the cubic or n to the n to the square. So these are also some complexity that you commonly could find in any textbook or literature. So I order them in the complexity order.
Okay, so it's the number of operations. I see. So there's probably a reference, for this categorization. Yeah, thank you.
Okay, thank you for all the questions. Let's move on with the talk. Thank you.
Yes. So because we have limited time, so I probably will just to show several examples of the performance of our methods. Here in the first set of category, in a set of the text in slide 5, the semi-traced feature set is what we did more operations on our molecular orbital-based features, because you want to satisfy the desired properties I mentioned in the previous slides. We did several additional operations on top of it. Basically, you want to make sure that when you switch your I and J index, you will have the same predictions for the actually, because they are the same identity of pairwise contribution of your MOs. So that's why we do a symmetrization in showing equation showing in the right, that you symmetrize the I and J orbitals to make sure that Fij equals to Fji in the features. And also we order the MOs to make sure that in each position that it represents the same identity, because recall that we extract the features from a matrix. So basically ordering is a flattening out strategy, that how we flattening out these matrix as a vector. And also we cap the feature length, because for smaller molecules you might have very few features, but for very large molecules you might have a lot of orbitals, so you have a lot of features in your feature vector. So that's why we cap the maximum number of the occupied orbital and the virtual orbitals that we include in this in the prediction in the feature set. So that's why we could have a consistent size for different sizes of the molecules. So this is important for us to transfer between different sets of the molecules. And for the first example I show here is a prediction of water potential energies. So basically we sample several water geometries or structures from molecular dynamics, and we could reconstruct the entire potential energy surface of water with very accurate. So this is uh, under 1 to around 1 to the 10 to the negative 5 milli-Hartree is similar to kcal per mole. So it's a very, very small, very tiny errors in our reconstruction of the potentials. So here we are using a Gaussian process regression, not neural network, because we're targeting to only using 100 structures instead of thousands of structures. So that's another thing that usually people are doing, that when they want to construct a potential energy surface to describe this molecule, when you have different bond lengths to have a very accurate energies, they will train thousands of the configurations or structures of this molecule and learn using neural net. But since we're targeting to high level accuracy theory, you cannot always compute thousands or 10,000s of the structures. So that's why we're using Gaussian process that require you only have 10 to 100 structures, and then you could have a very accurate potential energy surface. And also, I show 3 level of theories. As recall, the CCSD process T is the golden standard we targeting to, and MP2 is cheaper and less accurate. But we find actually we reach the same level of accuracy. So although CCSD process T is harder than MP2 to compute in the reality, but in our mobile mail, in our approach, they are the same hardness. So as long as you gave me 100 CCSD process T, I could give you very accurate potential. So, and the second example I show here is that I'm using small alkenes like anthene and methane and propenes to predict larger alkenes like isobutene and N-butene. So in this test, we find that our transfer test is pretty successful. So basically, our model has the ability to predict on small molecules to predict large molecules, and the figure shows the arrows of the absolute the arrows of our predictions relative predictions compared with the true values for the Bayesian data, and we see all the arrows are very small, and this shaded area is called chemical accuracy area. Basically, people are happy when all your data lying into this accuracy. So all our data is in this region, so we are happy. So we are very accurate. And usually DFT is also targeting in this region. So we're better than DFT because we're more accurate. And that's for the slide 5. And for slide 6, so like what I showed in slide 5 is a regression. So basically we have an energy target that we want to target to or regress or reproduce. But for the slide 6, I show some rationale for how to apply our molecular orbital-based features to understand the chemical space and supervisedly. So basically, you don't have any energy labels. You just have a set of the molecular orbital-based features, how you understand the chemical space. So on the left column, I show some pure computation results, no machine learning. So I plot the pair energies epsilon II, one of the pair energies, versus the feature value, one of the feature value, Fi, for 4 different molecules, and for the sigma bond in the 4 molecules. Although they are different molecules, we could see that the sigma bonds are all lying into the same line, and we could extrapolate with each other. So this support what I mentioned that before, sigma bond is sigma bond. So even though you have different feature values, but your functions is the same, or your trend is the same. So that's why we could extrapolate from each other and generalize our model. When you're training on water model, you could also predict HF, ammonia, or methane, because you have the same type of the orbital. You learn it in your machine learning model. But for Euro method, when you do a geometric representation, they are totally different. So you never trained on this molecule, so that's why you cannot predict it. And also, we find that like for all these molecular orbitals, they are pretty local, linear. So basically, if you see for within a short range, these are lines instead of a curve. So this could be a very useful property too for us when we study the molecular orbital-based features. And on the right column, I show a machine learning results using t-SNE. t-SNE is a high dimensional projection to a low 2-dimensional space with a preservation of the distances between the feature vectors. It's a very commonly used and supervised visualization tools in machine learning. So I'm visualizing the Elkin theories that I showed in the last slides of the unseen property and beauty. So so each dot represent one MO in this in the molecules, and different colors represent different molecules. And we could see a natural clustering for this plot that I also draw a line. So on the left is all the CH sigma bonds in all the molecules. In the middle are the CC sigma bonds in all the molecules. And we also see an extra group of the points. That is actually the CH sigma bond in the middle carbon. So when you have a longer carbon chain, say if you have 3 carbons, in the middle you will have a CH bond. But because this CH bond is slightly different than the CH bond that is directly connected to a carbon that never connected to another carbon. So that's why this shows up here. So only property and butane has this category of points. So that's why anti, you never see it here. So in this plot, we could find the first conclusion is chemical space could form a nice clusters. So similar type of the bonds will cluster together, or MOs will cluster together. And also, in different molecules, the same type of the bonds will cluster together. So basically, when you do a regression task, your machine learning model will feel this will be an interpolation instead of extrapolation when you predict butane using property and unseen, because it sees it in the training data. So that's why it makes our approach has a very powerful ability to predict large molecules using small molecules, because you see it in the small molecules. But all these results could also infer that we could use our mob features as a general tool to cluster the chemical space. So usually people cluster the chemical space using geometries or the molecule based. But here we're using a molecular orbital based representation. So our molecular orbital representations will be a new idea to think how you think about the chemical space. And also, based on the clustering, we could also construct some local regression models. Say, because maybe it is hard for you to regress a lot of data. But when you just regress a local cluster, which means I just regress the CH bond, it will be much easier for you to reach a very accurate model. Instead of I want to be accurate for everything using one regression model. So this will also scale our learning because GPR is a pretty expensive machine learning method too. So neural network is a linear scaling, but GPR is a qubit scaling. So that's the slide 6. And for slide 7, I might to skip it because we have limited time. But I just want to say that for the slide 7, I just pointing out some physics, some improvements for the features that I introduced to make sure that we have better physical performance in the feature set to satisfy more desired properties. And also, I introduce a scalable Gaussian process regression, basically the machine learning techniques we developed to learn a lot of molecules in the chemical space, like what neural network could do. Neural network could learn thousands, 10,000s of the molecules and generate a general model like a DFT that's applicable to a lot of things. But for GP, it is very hard. But we develop a new GPA algorithm to enable that. And I think the only useful thing in this slide for us is the figures I show here, the panel A and the panel B. Then I show that I learn on a 7 heavy atom, which is only have 7 carbons or oxygen or nitrogens in the molecule, could be considered as a small molecule dataset. And in the panel B, I showed using this small molecule trained model to learn a general larger molecule dataset called GDB13, which has 13 carbons or nitrogens or oxygens in the molecules. So basically, this is showing that our model trained on small molecules could be applicable to very large systems. And we have very high accuracy. The shaded area is what we consider chemical accuracy. People are targeting to, DFT are targeting to, and we could easily reach these highly accurate regions with only 100 or maybe 50 structures that we randomly sampled from the chemical space. And for the slide 8, I show the results for unsupervised clustering of the entire chemical space. Like what I mentioned, we could better understand the chemical space using our molecular orbital-based features. And here we again using these two data sets called QMSMB and GDB13, which are covering different types of the molecules in the organic space. And we plot the bond connectivity, the bond order, and basically the bond types that identified by the quantum simulations and also identified by the molecular orbital based features in the two panels. The out layer of this pie chart is the connectivity. Basically, if you're CH or CC or OH, something like that. And the second layer is the bond order. Basically, if we are carbon-carbon single bond or carbon-carbon double bonds, because they are different. And the inner layer is purely machine learning using molecular orbital-based features that we could see that, for example, for CH bond, that you only see 2 clusters for the CH bonds, although it takes around 40% of the entire chemical space. This is the most frequent bond MO type. And you find actually this right, the deep right cluster only has CH bond. It didn't have any CC bond, CO bond, no. And also for that deep dark purple cluster, it also only contains CH bond. And also we could find a lot of other examples. For example, the OH lone pair, which is the light purple color, it only contains the lone pair MOs on oxygen. So, and the same pattern we could find in the GDB13, which is a larger molecules, that we could see first, chemical speeds are very similar, even though you have larger molecules. Your bond frequency are still the same, because the Arctic rule or how we construct a chemistry molecules, right? So that's why you always have CH bond as the most frequent molecular orbitals or the chemical bonds. And also we see the same pattern and the same identity. So the same deep dark, same bright red cluster belongs to CH bond, and the dark purple belongs to CH bond, and it's the same pattern as what we see in the QM7b dataset. So this suggests that using molecular orbital perspective to understand chemical space is efficient and useful for us to see how well different types of molecular orbitals locate in the space. And imagine when you have a new orbital that you never know the bond connectivity or bond orders. You never seen it before. In a say you see it in a reaction, organic reaction, you cannot classify it. You could use our molecular orbital features and pinpoint a similar property MOs. So for example, it might be similar to a CN bond, a CN triple bond. Then you could infer the property of this new type of MO using your known properties that you know from the CN triple bonds to understand these reactions, to understand this process. And in the slide 9, I show that when we combine these cluster with a local Gaussian process regression, so basically I just regress each type of the clusters and to construct overall energy prediction, we still could provide the sort accuracy that we beat all the current literature in the world, that we could achieve the best accuracy and the best transferability to large molecules. So we see some other literature called DeepHF that is using the same cost. They are also using Hartree-Fock cost, that they compute Hartree-Fock and predict the differences and extract some, some energies or some information from the Hartree-Fock computations as their representation. So in the QM7b, which is what they trained on, they perform similar well as what we did. But when you apply it to a larger molecule, we could directly see that the accuracy collapsed for the literature DeepHF method, because they don't have the transferability in their setup. So that's why MobiMel is a very powerful tool in both unsupervised learning and supervised learning, even though you want to train a very large data set like what neural network usually work on. And in the slide 10, I just make a quick conclusion for what we did in this work. So our research goal is trying to merge in maximum physical knowledge that we know from the quantum simulation and quantum theory into machine learning, and generate a general tool for chemical applications. So for the physical knowledge, what we used, including firstly, we use the advanced decomposition, like what I introduced, the Nesby theorem, to first decompose the total energy as two components. One is Hartree-Fock, one is the correction, basically the correlation energy, and then we decompose the correlation energy as pairwise contributions, and we learn that pairwise contributions. Secondly, our molecular orbital-based representation preserve the chemical informations that provided in the Hartree-Fock computation, and also satisfy a lot of physical limits that I point out. For the machine learning black box or the applications, we create some regression models for the molecular energies. We also could do some supervised or unsupervised clustering for the chemical space to facilitate the exploration of chemical space and improve our chemical understanding for reactions, for any new explorations. And also, we make our machine learning model work for both small and big data regime. So basically, you can generate a mob-mel model as a DFT. Once you generate a large model, it can work like a DFT, like what I showed. And for the applications, basically today I just focusing on the organic chemistry, using the QM7B dataset and the GDB13 dataset, which represent different sides of the organic molecules. But I want to also mention that in our papers, previous publications, we also show several examples, including the biomolecule interactions, and also transition metal complex, and also transition states, etc. So we show different applications. It's not saying we are only working for organic chemistry. We're working for general applications. But today we just show the organic chemistry. So hope today I convinced everyone we are a physical driven black box, interpretable, accurate, transferable molecular modeling method. And we are at Hartree forecast to predict the golden standard CSD presses T or even higher level of the theory. And the last page is a lot of several developers in this team, my PI and the postdocs, Wellborn and Harsh, and Jasper is the graduate student, and also the previous graduate student, Sebastian, and another postdoc, Emiliano, and also several fundings we have.
Thank you so much for this amazing talk. This is so impressive. It's such an elegant technology that you have here. Thank you so much for presenting it so thoroughly. We really appreciate it. Yeah, if you have any questions, please flash your microphone, and we will take your questions. We have I don't know how much time do you have left?
Oh, I'm okay. So yeah, I think I could maybe do 30 minutes. I mean, I'm free. So I mean, if people have questions, you can free to ask.
Okay, thank you so much. I appreciate that. Okay, please flash your mics if you have a question.
So for the regression, are you regressing on the, let's say, the distance or the I didn't hear quite clearly. Is the feature that or the regression regressor that you're regressing upon? Is it like, did you mention like 200 features or something? I wasn't quite clear about that. Thank you.
Sorry, I'm not sure if I quite understand your question. So let me clarify if could you let me know if I'm understanding it wrongly? So you are asking, what the learning target, the pi energies we're learning from each molecules, are they sampled from based on a distance? Say basically we're dragging the molecules on a potential energy surface. So
Oh, okay, go ahead. Sorry.
oh yeah, go ahead. I mean that's what I understand. I'm not sure if that's your question.
Yeah, are you basically, I guess, regressing, let's say, the ultimate purpose is to get let's say, the strength of the bonds, the given any composite atoms, to see if they can form a molecule. Is that right?
No. We're directly regret. We are targeting to predict the total molecular energy of a molecule of a structure.
Okay, so basically, it's the total molecular, but the thing is, do you, so I guess not quite clear about the ultimate goal. So is it to, let's say, given, so basically you want to compute the total molecular energy, right? So let's say, is it the question, if given the composite atoms, these atoms, to is it to answer the question whether they can form a molecule, and then what the let's say ground state energy is? Would that be a correct statement?
No, we are not computing the atomization energies. So what you are framing is atomization energy. Say we are say something like we have atoms. When they form a molecule, there will be atomization energy. We are not computing the atomization energies. We are computing the total energies. And by decomposing them at Hartree-Fock theory computation and predicting the correction of the advanced theory.
Oh, I see.
Say
Okay.
like a DFT, you compute a DFT energy. So probably it's easier for you to understand the DFT. Say you compute the DFT energy of a molecule, and then you think DFT is not good. So you want a FUCI or maybe MRCI or maybe CC accuracy for this molecule. Then you compute a difference between your DFT computation and the CCSD computations. You find the difference probably is 1 kcal per mole. That is where your DFT is not accurate. And our machine learning model is predicting that 1 kcal per mole or maybe 10 kcal per mole, that you find the difference.
Okay, I see. So basically, it's a refinement on the, let's say, either Hartree-Fock theory or
Yes.
the correlation. Oh, I see.
Yes.
Okay. So I
So
originally I
it's
was thinking.
similar to Beast-Relay. It's similar to Beast-Relay, right? So Beast-Relay also you need to compute Hartree-Fock, and you did some other things to make Hartree-Fock better. So we are similar. We are refining the Hartree-Fock using the Hartree-Fock cost and giving you a very high theory, whatever you want. FUCI, if you have FUCI, we could do FUCI too. So if you have it, but we cannot compute FUCI, so that's why we're using CSD parentheses C as the example.
Got it. Got it. Okay, I see. I thought it was to actually compute the atomization and energy, and then see if they given the atoms, whether you can actually form a stable molecule. Okay, so right now you know they can form this particular molecule, but you want to get a higher correction to the energy correction to the Hartree-Fock plus the correlation, the exchange correlation function, right?
You could understand in that way, because I guess probably DFT it's easier for people to understand. But we are wave function theory, so it's slightly different. So it's not exchange correlation; it's just called correlation analogy. Slightly different because exchange correlation is more related to like column terms. But actually, for correlation part, it's not only the column term, something like that. So they are slightly different, but I think that understanding is okay. So to understand general idea.
I see. Okay, great. Thank you.
Hi, Jiashu. Please go ahead with your question.
Could I ask? I see all the MO orbitals are canonical, right?
Actually, I didn't mention that they are not canonical orbitals. They are localized molecular orbitals. Canonical
Okay, got it.
orbitals cannot work
I get it.
because they are not local. So this is another important idea that I didn't mention, but if people have interest, you could listen to this part. But if you think that's too advanced, that's okay. It's not affect understanding. So it is important for you to have local orbitals because all the Bob-Mail is local. Like what I showed, the local linearity plot in the unsupervised in the slide 6. You see that you need to preserve the local linearity or local properties to constrain everything into your molecular orbital. So it is important for you to using localized molecular orbital, not canonical.
Yeah, if you use localized orbital, I think it's feasible to try not the only one pair. You can try choose some like the 3 orbitals. At the third order correlation or fourth order correlation correction.
So your point is that I'm using two body decomposition instead of three body or higher body, but I want to point out that MO is a two body property, that three body decomposition is not meaningful at all, like what Nesbit theorem point out, that it is exact when you do a two body decomposition. Your three body interactions is inferred by your two body interactions. Say if you have three water molecules in the system, like a water trimer that interact each other, or maybe for a more general, like a condensed theory, like you have a lot of water in the system, they are interacting each other, and it will affecting your pair energies when you have a three body. So your pair
Okay.
energies will be different, and when you have and your Hartree-Fock will also be different. So it is all reflected in the MOs. So two body term is exact and sufficient.
Okay. So could I ask a final question? What do you think the error, where is the error is from? The missed features, or
The arrows. So there are several arrows from. So one arrows is about that the learning arrows. So we have a paper that in summation that showed we could do a QMNet, which is over 10 100K over 100K molecules with 9 heavy atoms, which is larger than what I showed today. So it's a very large molecule. We could reach 0.05 kcal per mole accuracy. So it's a limitation of your learning structures. That if you have a lot of structures, you can always improve the accuracies. But that's probably not that meaningful because you're from 0.1 kcal per mole to 0.05, that you require double of your training. So that's one error source, that you're not training enough. So you still have the ability to further improve your accuracy, but it's probably not meaningful, not worth that your inputs, efforts, your computational hours to generate this energy, reference energy. The second thing is about what I mentioned about the clustering thing. So when you trying to generate a general model, it is very hard for machine learning to learn everywhere accurate, right? So because it's a complicated thing, right? It's very complicated everywhere. So you need to figure out everywhere probably have different properties in different regions for different bound. But when you regress them together, so it is hard. So that's why learning itself is also having accuracy loss. So that's why when you break them down into small pieces and ask the machine learning to focusing on one type of the bound, it will perform better.
so now it's only for at most for a family of molecules, not universal, right?
I'm saying for universal. If you're saying for one molecule, we're rating the computational noise. So remember that 10 to the negative 5 millihartree, which is 10 to the negative 8 hartree, is generally most of the quantum simulation software could provide the precision. So we're reaching the precision of your reference theory now. So if you're seeing that we are just learning one molecule or two molecules, we are reaching the best. Actually, you cannot improve other the noise from your software.
Okay, thank you.
Does anyone have more questions?
I have one question, and thank you so much for sharing your slides. So you mentioned about the larger number of molecules, and I was just wondering about the number of the clusters, I mean, include of the diagonal and off diagonal. How you just estimate that?
Yeah, I think this is a very good question. That when you have a larger and larger size of training, you definitely will also have larger and larger number of clusters. So it will become an issue. Say when you have infinite learning data, you will have infinite cluster. That's insane, right? That's not agree with our chemical knowledge. So what we find is when you have probably like what I mentioned, 100K molecules, it's sufficient for you to just using the cluster trained with 10K molecules instead of using the 100K. So we think that only for the unsupervised learning part, when you do the clustering, you do have a limitation that you split up more and more, you add more and more structures and split up further and further. You didn't improve your accuracy because you reached a possible chemical type of the bonds. So actually, for the unsupervised part, you do have that limitations. But if you just have like what I showed here, 10K, you are not reaching that limit yet. But for further, you will reach the limit. So it will not be infinite. It will be a finite. And what we found in the practice is around 200 for the diagonal and around 1,000 for the off diagonal.
But it's still the, I mean, energy surface generate, right? In the same
Um,
pattern.
So this is if we are seeing clustering, that's for a general molecule. So for a general molecular data set, not for a one molecule potential. For one molecule potential, you don't need to do a clustering because they are following the same pattern. Clustering will not help you so much. But for different types of molecules, various types, various structures, you don't know if they are similar or not. You just regress them together. Clustering is helpful. But if you're just targeting for one molecule or few molecule potential, like a reaction, you don't have to do clustering.
Yeah, thank you so much for the question and the answer. Does anyone else has an additional question? No? Yeah, thank you so much for this really amazing presentation. And you mentioned, it was mentioned in the abstract that you have also that you have this improved prediction. Is there, since it's a mix of supervised and unsupervised learning, is there a way to? It's also mentioned that you have a way of basically telling how basically the results were computed. So is this approach a better way to look at basically causalities in the future? Can you apply this for other? Can you use this for other applications? This method, so that you can basically. It's very important to know how machine learning came up with their results in like more complex real world experience. Let's say, for example, if a hospital wants to know if a specific intervention helps patients more, would you be able at some point to use this type of machine learning to come up not just with a result but also why uh, um, the
Yeah,
model came up with it?
Yeah. So I think it's a good question. So you're asking for causality. So basically, there are two folds of the causality. First fold is why mob features could work so well. Is there any similar techniques that similar to mob features could also work well? Basically, if there is a causality of why mob features work well, then we could understand why these working well. I think this is the first fold of the causality. Second fold of the causality is if we could using the mob-mail results to understand the quantum simulation theories, like what we're learning, say like CSD Princess T. I think that's what I understand for the two folds of the causality. So if we say, for example, if we understand CSD Princess T, is there any way for us to using this technique to generate a new theory? to explore a new theory that if you derive from physics, that is so hard for you to explore a new thing. But is there a way for us to direct these people? I think that's for me two folds of the causality. The first fold causality, I'm thinking about say why this works so well, and is there any potential for this rationale could be extended to other fields, not only chemistry or biology, but whatever AI for science fields. I do think it could have the general idea or the soul of this work could be extended. So the soul of this work is not actually molecular orbital or, or anything else. It's actually the decomposition we are using. So basically, you are putting 99% of the knowledge that people have already figured out during the past 100 years into the machine learning instead of ask the machine learning to figure it out by yourself. Say I just directly ask it to learn the total energies, then MobileMail could not work well too, because you are asking machine learning to do so many things. It is so hard for it to learn directly. But of course, if you give it 10,000, 100,000, millions of data, it probably can figure out, but that's not really worth it. So that's why I think the soul is that we put most of the people knowledge into the model. We design everything based on the physics or what we have already known from this perspective to design machine learning instead of from a computer science perspective to design machine learning. We want to be very fast in the model, how to write the neural network layer. I think that's why we are more successful, because we're really using the people's knowledge to facilitate machine learning. So machine learning has an easier task. So that's why it can perform well. So I think this idea could be generalized in any area for science, physics, biology. So what people have already learned is still very useful for you as a baseline for machine learning. So that's one thing. The other thing is I think for our causality, for the other causality, say if we could help to feedback to improve to explore a new direction of the quantum simulations or the quantum simulation theories, like the theories I mentioned. I think there is still a possibility that the MobileMail can work as a debugging tool or as a direction tool. So in our development, so it's my own experiences. When MobileMail gave me some right warning, say I have very bad predictions. If I dig into the predictions, I could always find this MOs, this type of the MOs, or this structure has some issue. And then we work together to see why it has issue, and we can always find that this is an electronic structure or quantum simulation issue. So basically, we pick a bad simulation theory, or we didn't do well in our reference data generation. So this really happened in our previous experiences. So actually, we find this useful that the machine learning can infer your physical computations if it's reliable or not. I think MobileMail could be a very useful tool in terms of that. Say I develop a new theory, I don't know if it is reliable. We could try MobileMail and see if MobileMail gives you any red warning. Because when you just compute an energy, it's a number. You never know if it's reliable or not, other than you compare with another existing theory that say, oh, I agree with it, so I'm fine. So I think this will be another debugging tool for the new theory development. And also I think the idea that we are giving here, that we might be able to incorporate into a theory development, say using MobileMail to facilitate combined with a new theory, that a new theory based on MobileMail, that could be a physical development. I think that's another possibility for the causality.
Yeah, that's amazing. I really, yeah, I think that is really impressive. And yeah, I think in the future we will be really thankful for your work, because yeah, the causality I think is a big issue currently. So yeah, Yeah, it's really important, your work, so I really appreciate it. Thank you.
Yeah, thank you so much. I think a lot of AI for science people also notice that how you can understand or interpret the neural network is a very, very challenging thing. So usually you got something that it's not that meaningful, just a number, you don't know how to interpret that. So that's why we use Gaussian process and using this entire framework, because we could always interpret what we got. So Gaussian process, I didn't mention, it has uncertainty predictions. So if you have a large uncertainty applying an existing ML model, you find a very large uncertainty. It means that the model, the current ML cannot predict this molecule. So even though it provides you a number, so you don't know if it's true or not, if it's accurate or not. So our model has the ability to tell you that we warn you this number might not be true, might not be good. Especially for the case that you never have a real true value in your calculation. So that's a thing that most of the neural network based method could not achieve. A neural network give you a number, you never know if it is good or not.
Yeah, exactly. Yeah, I think that's really impressive. That's really very, very important. So yeah, thank you so much. And yeah, Frank, do you want to ask you a last question?
Oh, sure. Yeah, as well. I mean, thanks very much. And for that's the questions. The uh, so this is also related to computation. So have you utilized the popular methods like sparsification? I mean, I'm aware probably many zeros in your computation in order to improve performance. I mean, that's one, and also to just, I mean, because I'm interested in this work so much, I just want to learn more. So when you have the plots for the error, so could you just repeat how do the error is computed? I assume you're using the HF computation. Yeah. If you have more time, yeah, I do have more questions.
Yeah.
Thank you.
So I think the easiest question is the second one is about the error approximation, uncertainty approximation. Actually, it's directly from the Gaussian process. Gaussian process is a Bayesian method. So Bayesian method, which means that you have inferences and the confidence level for all the predictions. So actually, what Gaussian process predict is not a single point value. It's a at this point, it's a distribution. Say I only have a x vector. I predict it as it using the GPR model. Then it will give me a predictive mean, which is the Gaussian distributed mean of this your target prediction, and also a standard deviation of this Gaussian distribution. So if you think of each point as a Gaussian process, that's a little bit mathematical, but if you think it as a distribution, so actually all the predictions is for each point it is it's a distribution. So that's why you will have an error approximation, because you have uncertainty. So for the uncertainty, if you see the point, so Gaussian processor is a rigorous mathematical tool that it can guarantee to have a exact interpolation, because it's a linear algebra thing. So I didn't put the equation of Gaussian process in the slides, but everyone could see it from the Wikipedia that it is exact interpolation. But for the point, it never trained, which means it's extrapolation. It will have a wider distribution at each point to say that I'm not confident for this point. So that's why when you never see a molecule or this type of molecular orbitals, our model will directly give you a red warning that you have very large uncertainty, it might not be accurate. So this is from the machine learning techniques we are using, not the problem setup or the mob features or the Hartree-Fock based learning is not from there. It's from the learning. It's from the Bayesian learning approach. So that's the first question. Did that
I
answer
see.
your question?
So then with your contribution giving a linear cluster, you basically improve on that, right?
Uh, You mean you're asking for the leading cluster?
The linear cluster that
The
your work.
clusters. Yes. So the clusters that that when you train the supervised clusters with a new point, it can always assign a cluster. But if the points that you never see, it can only be assigned to the nearest cluster. It will improve your uncertainty, but still it will be larger than your normal points that you trained. You have already seen this type of the bound. Is that clear? So yes, that supervised clustering will help you to reduce the uncertainty because it will give you a closer model that might have a smaller uncertainty, but still compared with other points, it has larger uncertainty. So you still can tell if a point you have already, if your point, if you can still tell a prediction is reliable or not.
Right. So this is I'm just trying to get the picture from of your the abstract of your work. So the linear regression model that I assume that you're used to improve the. I mean, what
So
so
I think
maybe
you're
related
reading
or
the other
unrelated.
paper. That's I think you are reading the 2019 or 2000 paper that is very long time ago that will abandon that technique. Actually, I didn't introduce that in the paper in this
Oh,
talk because we abandoned it.
I'm searching. I got the paper from the link. Yeah, from the
Yeah, yeah, yeah.
info.
So we have an archive paper that we are still under review that using the most recent technique. So that technique, linear regression, that still works, but the performance is not good. So that's why we abandoned that technique. It's 3 years ago. So I think that probably the confusion where the confusion from.
Oh, sorry. I just to clarify because the room introduction has a DOI like link. So I like this
Oh,
title so much. So I actually download the paper and read a little. But anyway,
oh,
so
sorry.
thanks for the clarification. But the yeah my another question related to numerics techniques sparsification is basically supercomputing that to speed up your performance. But because I saw you have O n 2, O n O n square, O n cube, kind of a complexity
Yeah,
type of
yeah, of
arguments.
course. We're using GPUs. So if you read my slides, that for slides that I skip, that for the scalable GPR, I think it's slide 7 or slide 8. So for that, I mentioned that we are multi GPU. We could do multi GPU. Oh, it's slide 7 on figure. I said we are 6 hours on 8V100 DGX GPU from NVIDIA. So this is the commonly used academic used GPUs that we are only using 6 hours. And we are pretty good in terms of the multi GPU. So if you're one GPU, it will be 40 hours. So our multi GPU speed up is really good. So we could use GPUs and yeah, it's fast.
I see. Yeah, thank you. And yeah, I guess this respectful of your time, and I'll give the mic to Karina. Yeah.
Yeah. Because actually, for some techniques related to the Gaussian process or this numerical training, we have series of the publications. So MobileMail has around 5 or 6 publications. So today I'm trying to be more focused, to be more general. So maybe these papers are not in the links. So that's why people might have confusions. So for example, this GPU thing is not in the paper. In the current archive paper that Catalina posted in the channel, in the talk channel, we directly set this paper. So so the archive paper you're reading is also using GPU. So if you're using GPU, it's also very fast. It's even faster than this. We could train everything with 1 hour. So so because you have clusters, so each one is cheaper. It's just a speedy, very fast, like fly. So it's faster than neural network. I guarantee you, it's faster than neural network.
Yeah, thank you so much for this amazing presentation and all your explanations. Eli, did you want to
Yeah,
chime?
just really quick question. You were saying that you left some methods by the wayside. The October 2020 paper on transition metal complexes and non-covalent interactions, is that still current, or is that the stuff that didn't scale well?
For that the non-covalent interaction and transition metal complex paper, we are still using the old techniques. That's not October 2021. I think it's June, but not June, January, or
Well,
I think it's in the first half.
it's dated October 2020.
Oh, really? Okay, then that's why I don't exactly know the date. I was thinking it's 2021. Yes. For that one, we are not using these scalable techniques. But all these applications using these scalable techniques will give you the similar performance or even better performance. So we didn't come back to these examples because we just working on the benchmark that neural network people usually working on to compare with the neural network people. So yes, for the old papers you mentioned, it didn't using this scalable technique.
So follow up then. Are you have you or are you planning to take the current stuff that you discussed today and apply that to organometallics?
So the case is that I have already graduated, and and my PI has already left academia. Actually, he has already started his own company. So I'm not exactly sure. I'm thinking about a lot of things like doing excited states, and we are preparing stuff for OpenShell molecules and strong correlated systems. So I do think we have a very good potential to do organic metallics, especially when we have OpenShell paper published. It's still under preparation. Um, because actually what we reported in the paper you are reading is closed shell transition metal complex. But in the real reactions, organic chemistries, most of them are open shell. So we could do open shell too. So I do see this technique itself could do it, but for us, I don't think we have time to illustrate the examples. But for my personally, I want to do it. It depends on my new position if they support me to continue this direction or not. But I think if people ask me if you can do it, yes, we can do it, and I'm pretty sure it will be very good performance. And we do but we do not have any more time. So that's the issue.
So yeah, organometallic complexes, and especially open shell calculations, which are the really challenging ones, are an area of interest. And if I get funded to carry on some work in that area, and you are able to, I would certainly be interested in potentially collaborating.
Yes, of course. I'm happy with any collaborations. I think for collaboration that should be fun. And I'm also, it's also thinking depends on my new positions definitely. But I mean, for the general electronic structure theory, I still have the ambition to keep working on uh this type of work. Not only mobile mail, because like I mentioned, this could infer you for more general featurizations or design, like atomic orbitals, like Slater determinant, whatever. All these are possible, and we do have a lot of like polynite using similar type of ideas. So I do see we could do collaborations in the future. Oh, sorry, I must leave. Someone is knocking the door. Oh, okay. Someone's knocking my door. Could we just end
Thanks so
here?
much.
Okay, thank you so much. I really appreciate the time you gave us and the explanation. And
Yeah.
congratulations on your work. And I wish you all the best for your new position. Maybe you come
Thank
back
you.
with
Thank
updates.
you.
Thank
See
you so
you,
much.
everyone.
Bye.
Bye.
Enjoy your Saturday.
Thank you. Bye bye.
Yeah, thanks everyone for coming and asking great questions. If you want to continue to chat a little bit, it's fine with me. Like, yeah, but yeah, thank you for yeah, for this being part of this room. I was very impressed with her and her work. I think it's really cool and really important. And yeah, we'll have. Oh, Eli, go ahead.
Yeah, so like so many times over the years I've wanted to like, find improvements in quantum chemistry calculations. I'm really stunned by the power of extracting features from just from the Hartree Fock, and using machine learning on molecular orbitals. I mean, it's certainly a place that I had thought about going, but like, it's just it definitely exceeds what I would have expected. So I just want to kind of comment that this is really encouraging and kind of inspiring in like a nerdy sort of way.
Yeah, I agree. Yeah, she's amazing. I mean, her work is amazing, but also she is so smart. It's unbelievable. It's really impressive.
Yeah, I mean, I also on Eli's comment. This is a fascinating field, and I just wish there's more time for this very interesting discussion. Maybe the next time, and we can invite her back and to teach us more of the. By the way, I don't know if it's relevant because I got the I'm forming some kind of geometry kind of pictures of the my by based on misunderstanding the linear somehow I thought her work is based on the kind of a pairwise linear distance type of extraction, the features. I was just wondering if that's universally generalizable. But anyway, it maybe I'll back channel her, or, for this.
I think in general it is. That's what I understood also from her answer. I mean, I asked regarding causality issues with AI or machine learning, but I believe it would be. But yeah, I really like the also the part about the causality that she can really tell if the result is the number that comes out is accurate or not, because that's really something people struggle with a lot. So also for that, it's a really wonderful approach. So I was really impressed.
I might actually follow up because this for me I have a little bit understanding of the unsupervised learning, because that's more of a kind of a factorization type of approach without really objective functions, value functions, like supervised learning. I wonder if this her approach will be adding a good factorization tool sets to the current, most prevalent, like or be it a neural net or whatever supervised learning algorithm that already showing great potentials. It's like Alpha, the Google kind of chemical space exploration. I think that's something I have assigned a homework for myself. Yeah, Eli. I mean, I'm also looking forward to more discussions of this type with you as well. Yeah, thank you.
Yeah, so Katerina, I don't know if you ever saw the deep mind density functional paper.
No, I didn't.
It's pretty interesting. Unfortunately, it's not open, or the code isn't open, or excuse me, the code is open source. Unfortunately, I have not had the time to try and get it up and running, because I have to like install GPU drivers and stuff like that. That's painful on my rack servers. But it would be interesting to hear from people who are working on that. Or there's another quantum chemistry group also at Caltech. I forget the name of the group, that has some closed source but very interesting AI-based quantum chemistry stuff. I forget the name of the group.
Yeah, just send me either the link to the group or the paper, and I'll try to invite them.
But yeah, we also gotta nucleate something on fetal serum free media.
Right.
We can make that take off and support some real endeavors.
Yes, exactly. That's the plan, right? That's the plan that we are working on, to come up with something that's useful and makes money, to have money to do whatever we think we want to do.
Our agenda.
Exactly. And find a lot of people that are interesting to collaborate with. So yeah, I agree. Let's work on that. I still don't think it's that hard, but
I think that it's going to be an issue with specific cell types, that don't completely support themselves with anything unique that isn't. In other words, when they need some unique growth factor that isn't autocrine. That will probably be an issue, but at the same time, if it's an issue, then it's an opportunity to learn.
yeah, and then we would finally know at what stage um, cells would need something really essentially. We would also learn basic science, physiology.
And there are likely to be things that depend on the right level of insulin, or depend on the right thing coming from the pituitary, or so on and so forth. But again, wherever we find frustration, there's like an opportunity to learn something important.
Yeah, in FPS there's definitely insulin in there, and yeah, so I agree. We would learn which cell type differentiation would need what type of what type of ingredient would be essential for them, and that would give us a lot of insight into what for developmental stuff it would be really interesting. And also then for malnutrition, we would know at what age maybe, and what stage of development special nutrition elements would be really crucial. So yeah, I think we could learn a lot from that. And that is probably, when you write that for a federal grant, that's what would get you the federal grant, like NSF or something. The part, if yeah,
Yeah,
you
so
have
Carla's very interested in pursuing this, so we need to just schedule a time when she can join us. And maybe we should also try and figure out who else with a mammalian cell culture background might be interested.
yeah, definitely. I mean, yeah, I have some, but I'm not. I wouldn't say I have a name in. It's also important to have somebody with a name to get these grants in that field, with a lot of publications in the field. So should should check for that. We had a few stem cell differentiation speakers, and we will have some in the future, I think. So um, yeah, we could maybe contact somebody for that. Yeah, we'll have just to summarize really quick while people are still here. We'll have tomorrow the weekly recap, and then on Monday we have a room, but we might have to reschedule. I'm not 100% sure yet. But so far, the room on Monday is about telomere to telomere and human repeat elements. So it's about this non-coding repeat element DNA in the telomeres. And then we'll have Dr. James Tour about using plastic waste products to capture CO2 in nanopores of plastic waste. I think
I'm definitely looking forward to that because I mean, Tour is like he's you know a very very well established researcher, and like I don't know if this is one of the things that I'll be asking him about the Joule heating based graphene fabrication. And if anybody hasn't seen the paper, there's this paper that they published, I think like a year ago or so, where they talked about or they showed getting graphene from just like a whole range of materials, including low value material, which was vegetable waste, and then like negative value material, which was dog poop.
how interesting. No, I didn't see that. I didn't know about that paper. Yeah, I'm glad. He said yes, he was traveling a lot, and then he was sick for a while, but gladly he feels better and can make it on Tuesday. And then we'll have Wednesday Dr. Morrissey. It's a doctor that discovered a new type of human lung cell related to like COVID research that was just discovered. It's really curious to see that we still don't know every single organ and cell type in our own bodies. It's it's quite impressive that like in the last years we still get these new insights. And then we'll have Dr. McGuire on Wednesday. Complex molecules that have never seen before in space. And on Friday we'll have Dr. Oshie Weller from the UK coming talking about he developed a varroa-resistant honeybee. And he will talk about why varroa is so threatening to bees and how to basically make them resistant to it. I think it's really important work. We need our bees. And yeah, that's our next week. It's a little bit less busy than this week, but this week was crazy busy, so it's actually more manageable. So we have one double room day, and then 1 or 2 days no room, and and then on the weekend we can have maybe a discussion about our side projects and interests that we have. So that's also fun to have some space for that. So yeah, I'm looking forward to it. Thank you for coming, everyone, and enjoy the rest of your evening or morning or middle of the day, wherever you are. And yeah, hear you soon.
Thanks,
Thank
Katerina.
Thank you,
you.
Katerina. By the way, I see our previous excellent speaker Rupesh in the among the listener. I wonder if he would like to join us one of the these future sessions. Yeah, you're very welcome. Yeah, by the way.
Oh yeah, Rupesh, anytime. Oh, he's coming. He's coming now. He's joining. Hi, Rupesh. How
Hi,
are you?
Rupesh.
Did
Hey Frank, hey Katrina. I'm good. How are you guys?
good. Nice seeing you.
Don't know how long
Oh,
have you
yeah.
been listening. Were you what's your impression? What's your any comments?
Uh, I didn't like. like get to come in time. I was kind of late, so didn't hear much about the talk. But I was going through the PDF and meanwhile watching NBA as well. So I'm kind of in between. Can't say anything.
Sure. I mean, you're very terrifying, given that you're in the probably related thing.
But yeah, it was kind of related. That's why I was like trying to understand what it is.
Yeah. So I guess this time we'll, waiting next time to join us for web
De-
infinite discussion. Yeah. Thank you.
yeah, I definitely would like to join. Thanks, Frank.
Okay, thank you. Thank you for stopping by anyway. And yeah, we'll have a short summary tomorrow of the rooms. If anyone missed rooms throughout this week, we'll do a short summary, which is always kind of rewarding also to like recapitulate what we learned this week. So I think it's always interesting. Okay, thanks everyone. Enjoy.
Bye bye.
See
3,
y'all soon.
1, bye.